All right. In the last lecture, what we saw was we looked at the case of hash families, which are not purely random. We saw all the analysis of hash functions using uh, hash functions that were purely random. And then in the last class, we saw what happens if the functions are not exactly random. Right? And to that end, we studied the notion of universal hash families. And in particular, we analyzed two universal hash families. Right? And uh, we said if you use a two universal hash family instead of a purely random hash function, how does the analysis of the balls and bins paradigm change, and consequently how does it affect the worst case complexity of say hashing with chaining and so on. Right? So that's what we did last time, and then we said finally we looked at this the hashing problem where you want a data structure for the static dictionary problem. Right? This is where we were in the last class. So we are looking at this problem known as the static dictionary problem. And what you have is that there is a universe U, and you're given a set S from the universe, right? So you're given such a set, and what you want to do is you want to store S in a data structure so that you can perform um, membership queries. Right? Membership queries are queries of the form is X in S, right? Efficiently, right? So what do we mean by that? We want the data structure to use minimum space, and the complexity measure is the number of queries, right? And to that end, we define the notion of what is called the perfect hashing. So what was perfect hashing? So a perfect hash family, right? So we define what is known as a perfect hash family. A perfect hash family is a set of functions H, right, from the universe U to some set N, such that for every S subset of U, such that say cardinality of S is equal to M, right, uh, there exists a perfect hash function for S in the set H, right? And what do we mean by a perfect hash function? This is one with no collisions, right? So this is injective on the set S, right? So this is the idea of perfect hashing. And so the goal is you're given the set S, and you know that there must exist perfect hash functions, right? So for any S, there will exist a perfect hash function. For instance, if you have cardinality n is equal to m, then you can always have an injective map from S to n, and for every S you can have such a function, right? So you can collect all such functions, and that will form a perfect hash family. But what makes this problem interesting is that you want to actually find the perfect hash function for S efficiently. If I tell you what S is, you should be able to tell me what is the perfect hash function that is going to perform this, right? That will help me represent S in an efficient manner, which will reduce the complexity of membership. Right? And what we'll so we did see a little bit of we analyzed two universal hash families, right? So what we said was that uh, so if you pick H uniformly at random from a two universal hash family, right? If you pick h uniformly at random from a two universal hash family, and n is something like order m squared, then h is perfect, right? Or you can say that then the, in other words, it's not perfect, but you can say that then the expected, uh, or rather with then with probability at least half, the worst case query time is order 1, right? This is what we saw in the last class, right? And the analysis was just counting the number of collisions when you take a two universal hash family, right? And this is something that we saw. So for instance, if you have order m squared space, if you use order m squared space, which means you have a table, a hash table with order m square entries in it, then you can actually and if you use that, then definitely it'll have with probability at least half, its query time is going to be order 1, right? This is something that we saw, right? Any questions so far? Okay, so what we'll see now is a data structure. So we are going to, the goal is to obtain, we want to represent S in order cardinality S space, and the query complexity is going to be order 1. Okay, and this is what is known as uh, Fredman Komlosh Zemeredy, right? Usually called FKS hashing. Right? It basically solves the problem of representing a static dictionary where in sort of like the optimal space and with query complexity order 1, right? So this is from the 80s. Okay, and what we'll see is that we have everything actually available with us to explain this. So we'll just briefly explain. We will briefly go over what how this hashing works. Okay. Any questions regarding the setup of the problem, the results obtained, and so on? Any questions? Okay. So then let's see how we do this, right? So the idea is that if you were to use one table, then definitely we'll have to use order m squared. That is sort of unavoidable, mainly because of the birthday birthday paradox, right? I mean, you'll have so many, you'll need at least this, that if you use just one table, then that is not it's not going to work out. You will definitely need something like a square. So the idea is to idea is to use two hash tables. Okay, so what Fredman, Komlosh, and Zemredy do is that they have a primary hash table, call it T. This is a primary hash table, right? This has size order cardinality S. Okay? And what they do is that corresponding to each entry I, they have a secondary hash table Ti. Okay? And the length of this would be, so if there are say so the length of this is length is such that collisions are avoided here, right? So here you will have something like the square of the number of collisions. So you have two hash tables, right? One of them hashes into the primary hash table, And then each primary hash table is a pointer to a secondary hash table. And when you want to search, you first search in the primary hash table and look at which is the secondary hash table in which that element occurs, and then you go and search in that secondary hash table, right? So there are two things to do here. One is how are the hash functions selected, right? So you can think of, for now, you can think that there are these functions. There is h. This is the primary hash function, right? And then for there are hash functions h1, h2 up till hm, right? These are the secondary hash functions, right? So for instance, you have these are h1, h2, h3, and so on till hm. Okay, so m, m is order s. M is equal to cardinality s. Right? It can be order m, but let's take it m for now, right? So we'll see how to choose these families, these functions. But now the querying is as follows, right? How do you query? So given x, you compute h of x, right? So when you compute h of x, you go, you look at this is some number between 1 and m, right? And then you take, so say h of x is, oh, sorry. Let's write it again. So you're given x in the universe. You compute j, which is h of x, and then you query hj of x. Right? So that's the queries that you will do, right? You will first check whether you will first find the entry. This is the uh, entry in the primary table in T. And then you go and search in the corresponding location in the secondary table. So there are, you're just doing two queries based on H. Right? So the querying is just as follows. If um, so this will work provided there are no collisions in. So this is basically assuming no collisions in the secondary tables. Right? Any questions so far? Okay. So so let's see how this will work, right? So notice the following. So the first, what do we know? So let's so what we are going to do is that we are going to have h. Okay, this is going to be a two universal hash family, right? So you can assume that the you can take your pairwise independent hash family for now, right? That's even strongly two universal. Right? So that is so you take this h, um, and now what you will do is initially, so say you choose so this h initially is the set of functions h from m to sorry so it's going to be from u to m, right? And what you want to know is what happens to um, how does so when you map S to the set, how many collisions are there, right? What is the maximum load? So if what we saw that if so when you map this, so you can say that for every I, you can say bi is the set of elements x in S such that h of x is equal to I. So where h is picked from this hash family. Okay. And say that the cardinality of capital Bi is given by small bi. Right. So this quantity is the load in the bin I, if you want. Correct. And the if you were to use chaining, then the length of this size of this Bi is your time complexity. Correct. So now what we do is that, so we know the following, right? So from the analysis of the two universal hash family, here is what we already know, right? So let me just write this, right? So if m balls are thrown into m bins, thrown into n bins, right? Uh, using h that is picked from a two universal family, then and so let y be the maximum load. So what do we know? We know that the probability that y is greater than m square root 2 by n plus 1, this is at most half. Right? This is something that we saw in the last class. Right? This is what we know. So now this means that if n is something like order m, okay, so this is what we have, right? And so now so what do we have? So now what we are going to do is that we are going to pick um, so this max load is yeah, so this is the okay, this is what we have. So now what you do is we are going to map the elements into each the set of elements that are mapped to, say, the bin Bi. We are going to consider map it into the corresponding um, new hash function, new table, right? So for that we need a different hash family. So again we are going to use so now the final mapping from, so the TIs, right? So these mapping is again going to be from a two universal hash family. Right. So what do you have here? So let's say these values are b1 b2 up till bm. So you have so many bins. Now what so let x denote the number of collisions, right? When m balls are placed in n bins, correct? In m bins, using a two universal hash family. So if you recall, we said that this probability, right? This probability to be, so how did we calculate this? So we said that expectation of x was the summation over all these expectation of xij, right? Which is whether there is a collision between xij, basically is telling about whether So this is whether there is a collision between balls I and J, right? And in particular, what we saw was that it's in a similar vein. What we saw was that the probability that X was so we could bound the expectation of X, right? Let me say in the general case, let balls are placed into n bins, right? So expectation of X was bounded by m square over 2n. This is something that we saw in the last class, right? So therefore, what we can say is that the number of collisions X, the probability that it is greater than m square over n is at most half, right? Which means that if you were to use a two universal hash family, then so now what are we doing? So what is the value for value of n now? Since we are using a primary hash table that has size m, this is equal to m, which means that the probability that X is greater than m is at most half, right? Where X is the number of collisions. Correct? So now what you do is the following. So now you know that the number of collisions is m, and recall that each bin, right? Each bin bi has a small bi number of elements mapped to it, right? And what was our idea? What was our hash? What was our data structures? The secondary tables are uh, hash tables of length bi squared, right? So the total space used by the structure is something like order m, right? This is for the primary hash table, plus summation over bi squared, right? Each of these are this is the size of the secondary hash table, right? And now this is not going to use more than order m space, because you know that if you choose the correct hash function, right, where the number of collisions is at most m, then what you can do is what you can conclude is that the number of collisions is actually upper bounded by summation I equal to 1 to m is actually equal to bi choose 2, right? Because bi is the number of elements that are getting mapped to the table entry ti, right? So which means that bi choose 2 elements are colliding into index I. Similarly, there are positions 1 to m, so the number of collisions is bi choose 2 summing over I equal to 1 to m, right? And this is at most um, this we know is the number of collisions is actually equal to m, right? Because is at most m, right? So we are choosing a hash function, right? This is because we are choosing h such that collisions is at most m, right? And this would mean that this implies that summation bi squared, right, is actually order m. So therefore, the total space that is used by the data structure is just order m, right? Any questions on this? So there is only one small thing, right? So we have worked under the assumption that our hash function has the property that the collisions is at most m and so on. What we actually have is a family of functions. We have a set of functions. We know a way to sample from that set, right? So if you recall the way of the pairwise independent hash functions were created, you have a set, and the way you sample it is you sample those two elements from the finite field, and from that you get the hash function, right? But now you need to actually, given S, you need to actually construct get hold of the actual hash functions H and HIs. So how do you do that? Right? So for instance, at this step, right, at this step here, we have assumed that the primary hash functions is causing only at most m collisions. So how do you get hold of an actual hash function that is going to have only at most m collisions? What you have is a collection of hash functions, right? Now you want to get hold of one hash function which has the property that the number of collisions is at most m. How would you do that? Because that is what is finally needed, right? When you want to implement the data structure given S, you need to get hold of the hash function for which the number of collisions is at most m. How do you do that? What is a way in which you can do that? Is the question clear? Yeah. Right. What we said was that if you sample from a pairwise independent hash family or a two universal hash family, then with probability at least half the number of collisions would be at most m, right? But now given a set S, you need to get hold of this hash function. How do you do that? You can think of a randomized algorithm that will do that with, say, high probability or something. Any ideas? Right. I want a randomized algorithm that with high probability, with some constant probability, will always output a function for which um, for which the collisions is at most m. Right? Or I want to be sure. So for instance, I need to make sure that when I get hold of a hash functions, it must have the property that the collisions is at most m, for instance, right? So can I do it efficiently is the question. So, how do I do it efficiently, in other words? If the question is unclear, please let me know. Otherwise, what do you think? Does this suggest something? Whatever is written here, does this suggest something? So if I sample from the two universal family, how many times should I sample before I can hope to see such a hash function? Yeah, yeah. So Sarthak, what he's saying is correct, right? So you pick a random hash function, you pick a function from the hash family, and you check the number of collisions, right? Because the set S is given to you. And for this particular hash function, you see what is the number of collisions, and you check whether it is less than m, right? And so the random variable which corresponds to, so this is a geometric random variable, right? So what you have is a geometric random variable, and what you need to do is that in expectation, you just need to pick two times, right? You need to repeat it only two times before you will see a hash function for which the number of collisions is at most m, right? Because this tells you that the probability that x is less than or equal to m is at least half, right? Which means that if you do this repeated twice, then you can hope to actually see such a hash function, right? So you just do this 2 times, and maybe more than some constant number of times, and then you will get hold of a function where the number of collisions is at most m, right? And then what do you do then? So you basically sample h uniformly at random from the 2 universal family until you find an h such that number of collisions is at most m, correct? And then what do you do? Then you do this, repeat this for each I in m, right? Because what you will do is, yeah, because so once you do the step here, you can compute the BIs, right? If you get hold of the function h, then you know what the values of BIs are, because you can actually you know the set S, you can explicitly look at the collisions, and you can get hold of BIs. And now what you do is you sample again from a pairwise independent hash family. So you do this at this step is again sampling h from a 2 universal family, right? For each I, you sample h from a 2 universal family, and so that number of collisions is equal to 0, right? There are no collisions, right? And the same analysis tells you that the probability must, here also you need to do how many times? You need to do at most 2 times, right? In expectation, you need to do it 2 times before you actually get hold of such an h. So you do this for each of the buckets, and you have this set of hash functions h and h1, h2 up till hm, and this will be a and you use these hash functions to represent your set S, right? And to construct, so therefore, what is the time for constructing the data structure? The data structure, right? Again, it's not a deterministic process. It is again randomized, so it will be with some probability. But what will be the time? Okay, so you can just check, compute this. You just leave it as an exercise, right? But it is very efficient in terms of the size of the set S that you're working with, right? And so with that, we have the data structure for storing S. And then as we described here, right, the queries can be performed, right? Once we have this data structures with us, then the query is just taking order one time. So you use these 2 levels of hashing, right? Both with 2 universal hash family, and the result follows from the analysis that we saw, right? You're just looking at the number of collisions, and in the first table, you have many collisions. You have at most m collisions, which you distribute among the secondary hash functions so that there are no collisions in the second level. Right? That is the idea. Okay? Any questions regarding this FKS hashing and its analysis? Anything that is unclear, or any other comments or questions? Okay. So then, so we have seen, so this analysis has mostly been, sorry. So we have been looking at hashing, but mostly in the scenario where you have hashing with chaining. And all this analysis that we did was basically looking at the case where what is the largest chain size, and what is um, the time complexity depending on the chain size, right? So there are other ways in which you can do hashing, right? So what is some another way which you probably know, which you have seen before? Right, hashing with chaining and something else as well that you've seen before. Instead of chaining, what is another way in which you can, yeah, open hashing, right? Open addressing, right? Something called hashing with open addressing, right? And what is the idea between in hashing with open addressing? So in this case, uh, what you do is you represent all the keys in the table, right? Without using any secondary tables or chain linked list. Right? So you have one table, and then if you get an X, you try to map it to some element, some entry in the table. If that entry is filled, then you try to find a different position in the table and do it, right, and put it there. Right? So the thing is, how do you find the alternate locations, right? If you're trying to you have a hash function, you map it to one entry in the table, say that is filled, then which how do you choose the next place to search whether it is empty or not? That is what is uh, interesting in this scenario, right? So you have this, say for instance, in a very what's happening. Right? For instance, say you have m items, m elements to be hashed into m locations in a table, right? So you can assume that there are hash functions h1, h2 up till hm, right? And then what you do, what is this? And then what you do is, given x, right, you put you try h1 of x and store x in h1 of x if it is empty, and you keep searching, right? You keep searching for h1, h2 and so on, right? Find the smallest I such that okay, such that hi of x is empty, and store it there, and store in t of hi of x, right? And searching would be basically uh, search search in hix, t of hix iteratively, right? Right? Until you find x. Else say that x is not in S. Right? Uh, this is the basic idea of open addressing, hashing with open addressing. Right? Just a few things. One is that it is possible that h1, h2, hm might all map into the the same uh, location. You want h1x, h2x all to be mapping to different locations in the hash table, right? So what happens if you use open addressing instead of hashing, right? So instead of chaining, right? So this is something that you can. So what are the assumptions that we actually idealistic assumptions that we can make, right? So in the case of chaining, the idealistic assumption was that H was a random hash function, right? Here, if for the most idealistic analysis, which is also a very bad analysis, is usually that you will assume that HIX is uniformly random, right, for every I, which means that X is mapped to the location, any location, X is getting mapped to uniformly at random. And then a secondary assumption, which is even worse, which is that H1 X, H2 X, and so on till HMX is a uh, uniformly random permutation of the set 1 to M, right? Not only are HIX purely random, but these different functions are, it's like a uniformly random permutation of 1 to M, right? It's like saying that the locations where X can possibly go to, that's a purely random, it's like a random sequence. So you have M elements that you want to put it into this array, and there are M locations. So these M hash values are like a uniform permutation of 1 to M, right? So the sequence in which you will search for where to put X is as though it's like a random sequence. That's what it is saying, right? So these are very strong assumptions, right? These are very strong assumptions, and under these assumptions, for instance, if you analyze open addressing, the expected running time, right, for searching and inserting, right, for searching is something like 1 divided by, or for instance, if you're search putting, say, um, m elements into an n element array, what you have is something like n divided by n minus m, right? So if you write this is 1 divided by 1 minus m over n, and this is the load, right? This is the load. So if, for instance, if the number of elements that you're input, so for instance, if m is something like 2n, right, which means that you have an 2n length, you have a sorry, n is like 2m, which means that you're entering m elements, but you have an array of length 2m, in which case your expected running time is basically, in this case, the expected running time is just order 1, right? So as long as the hash table is not very full, uh, under these assumptions, what you have is that the expected running time for searching is just a constant, right? If you use open addressing instead of chaining, right? But so this calculation is not very difficult to do. I will You can just try it. Otherwise, we'll see it later, right? But naturally, this assumption is very strong, right? These are very strong assumptions. But so, do you know of? Have you seen any open addressing schemes? What is the most common open addressing scheme that you might have seen? We have seen it before in some other course, right? Or if you might have even implemented a hash table hashing scheme which uses some open addressing schemes. Anything that you have seen before? Linear probing, right? So one such, as Pragyan says, one such thing is what is called hashing with linear probing. So what does linear probing do? So the linear probing, the idea is the following. So you have a hash function. So h is a hash function. Okay. So now what you do is, given an x in the universe, you find the smallest I, such that so maybe not the smallest I. Given an x in u, you first see whether h of x is empty or not, right? Or you put it there. Otherwise, you look at h of x plus 1 modulo m, which is the modulo n, right? This is the length of the size of the table, correct? And if that is not empty, you look at h of x plus 2 mod m, mod n, and so on, until you find the first location where you can put it. Yeah. And searching is also easy, right? How do you search? You check h of x plus 1, and so on. So if h of x is t of h of x contains x, then x is in S. If one of the entries is empty, then x is not in S, right? Because these are the possible locations where you could have put h of x plus I. If there exists this t of h, there I says the t of hx plus I is empty, then x is not in S, right? You start from h of x, you see whether that is equal to x. Otherwise, you go to the next one and so on until if you find an empty position, then you know that x is not in S, because if at all it had existed, it would have been in one of these positions, right? So this is a scheme where instead of using different hash functions, you have a very deterministic rule of placing elements into the hash table, right? So now you could ask, how does hashing with linear probing is something that is very constantly. I mean, it's a very simple enough rule, and it is used and practically it's very useful as well, right? So you could ask, how does it perform, right? What is its performance? So once again, you can do your standard analysis if you want to do, right? You can assume that H is truly random, right? Assuming S is truly random, what is the expected search time for hashing with linear probing? Right? Suppose H is chosen uniformly at random, and then you use the linear probing for hashing, right? Use it for the open addressing. So what is the expected search time? Right? So it turns out this is order 1, and this is a very famous note. It's from Knuth in 62, and it is generally considered as sort of like the beginnings of analysis of algorithms. It is sort of like the first notes, or it's not exactly, I don't think it's a published paper, but it's one of the first notes where you have a formal analysis of a algorithm, right? So it's usually generally considered like as the starting of formal analysis of algorithms. Right? I'll give you a reference for this if you want to read. The nice thing is that the analysis is very elementary, right? It's you don't need to know any advanced math to understand it. The analysis is complicated; it's not easy, but you don't need any additional knowledge of any advanced math, right? So if you have, if you want to use hashing with linear probing, then if you assume that h is a truly random function, then indeed you have you get expected constant time, right? But if you think back on whatever we have done so far, we want to know what happens if you don't have a truly random hash function, right? And it turns out that you don't need full randomness. What you need is if h is 5-wise, like, so just like pairwise you have 3-wise, 4-wise, and so on, 5-wise. If h is 5-wise independent, then the expected search time is again order 1. You don't need full randomness. So all you need is just 5-wise independence, and that is sufficient for getting an expected search time of order 1. Furthermore, if h is just 4-wise independent, then the expected search time is not order 1. It cannot be order 1, right? You don't have constant search time, right? So 5 eyes is what you need, and 5 eyes is necessary. It's necessary and sufficient. And this is a set of results from 2013 and 2015, right? These bunch of results which shows what is actually necessary and sufficient for hashing with linear probing. And this is one of the reading materials in one of the course projects. And I think one group has actually selected this as their what they're going to read. So I'll not spend much time on this. You will hear more about it when they present their report, right? About these topics. Okay. So we will stop for now, right? We will stop with for this for now, and we will continue again with other topics related to hashing, right? Which on in the next class. One small announcement: I think you probably know that Wednesday we have Friday's timetable. Right? That's what is written in the academic calendar. So then we will not have a lecture this Wednesday. Instead of that, we will meet on Thursday, right? So Thursday 3:25 is what when we'll meet next, and we will see some other hashing techniques, right? For instance, we will see a technique known as cuckoo hashing. We'll first see that instead of using a random function, if you choose two positions at random and then choose to hash into the position which has lesser number of elements, then you get considerably improved guarantees on the length of the chain. That is something that we will see. Then we will see other hashing techniques. One is known as cuckoo hashing, and then if there is time, we will look at hashing for geometric problems, right? What is known as locality sensitive hashing, right? So depending on time, we will do these things. And with that, we will close the second module of the course, right? Hopefully this will get over before the mid-sem. Okay, so that is the plan. So there's no lecture on Wednesday. We meet on Thursday at 3:25. Okay, any questions? Any questions? Okay, so then I think we are done. Yeah, thank you.